Hi, everyone. Good afternoon. Thank you for joining us for another Ironside Take 30 with a data scientist. I'm Pam Laskar. I'm the Director of Data Science at Ironside. And today I'll be talking about an AI and ML 101. Just meant to be kind of light and interesting. No math, maybe a smidge, but it'll be easy. Just to give you an overview, if you're a business leader or you're in IT and you just want to better understand AI and machine learning. I also want to just thank you for joining these in general. We've been providing these Take 30s as a way to make our experts available during this very challenging and unprecedented time in our lives. And I wanted to make you aware of a new service that we're also promoting. Down here, you see this website where you can go, and I will send this out after today's session in an email. But we're offering these one-on-ones with the data scientists. So our Take 30 sessions with data advisors and BI experts are doing the same thing, and you can go to our website and sign up and register, and it'll just take you to our calendar and you can sign up for a time slot. So if you ever want to talk more about any particular topic, or you want to talk specifically about your business or just get some thoughts, you can have these one-on-ones in addition to the Take 30s. So like I said, I'll send that out for you to know. Before I jump into things, quick commercial, right? We're here to help our clients use their data to make better decisions about their business. That's our mission, and we back that up with capabilities across the end-to-end data and analytics lifespan. So we have capabilities in advisory and strategy, in business intelligence, information management, data governance, and managed services. And data science particularly kind of sits across all of these wedges, and we work in AI advisory and strategy, designing, building solutions, managing, and hosting them long-term as well. So today's topic, bit of a mix of information about machine learning and AI if you're new to it. What is it, different types and methodologies. We'll talk about the data science process and then take kind of a deep dive into each of those steps in data science and summarize with some key takeaways. I also want to just let you know that we'll save time at the end for questions, and you can take yourselves off mute at that point and ask questions, and you can type them up. But at any point during today's presentation, feel free to type it up in the chat box, and Debbie will let me know if there's questions, so we can make this a dialogue. So first of all, I like to get semantics out of the way and just level set on terminology. People get a little bit hung up on these terms and start to either feel concerned if they don't understand the difference between machine learning and AI, or predictive analytics and advanced analytics. And generally, I just like to level set. So if we're talking about any of these things, we are probably in the same world. We're in the same universe. We're talking about a step beyond traditional analytics into a deeper and more advanced approach to business intelligence. There are some subtle differences between each of these, but one of the reasons I told people not to worry about that so much is because there really isn't a universal global definition. Every data scientist I talk to has a slightly different take on what these things mean. Predictive analytics, advanced analytics, machine learning, and data mining, these are methods, right, that move beyond those descriptive and traditional approaches. Artificial intelligence, to me, means when you take those machine learning algorithms that you've created with those methods and you implement it into the business, right? Once it's deployed, once it's in production, it becomes AI. And data science is the field of practice. So you can think about it that way, but again, I just want to level set because I will say machine learning one time and predictive analytics one time, and the difference probably is not important. So what is that step away from traditional BI? Well, you're probably very familiar with what we call descriptive analytics. That's most of traditional business intelligence. That's looking at, you know, what's the rate of customer churn away from my business? What's the rate of default or the average number of claims that happen in a certain population, right? That's just looking and trying to understand your data. As we grow in complexity and value, we get deeper and deeper into these analytics. So diagnostic approaches do something similar to descriptive. You're looking at the past, but you're drilling down into it. You're trying to understand root cause. You're trying to look a little bit deeper. You're hypothesizing about, well, what is causing customer churn, or how do I manage risk? And so you're looking for associations in your historical data with that metric and that KPI. When we move to predictive analytics, this is when we have to apply some more advanced techniques to do that drill down. So it's partially still driven by those hypotheses, but instead of looking at one variable impacting your KPI, and then later another variable impacting your KPI, you can throw everything in and assess it all together. And so you're understanding your business within the context of all of these multidimensional variables. And you can take it even a step further into prescriptive analytics. So once you start applying predictive analytics, you get these predictions about the future, and you can start to prescribe actions based on those. If you understand the propensity of customers to accept one marketing campaign over another, you can prescribe and automate that particular campaign gets sent to them. And so what we're talking about when we say predictive analytics, machine learning, AI is kind of in those top two tiers of complexity and value. And I saw this survey in Narrative Science that I thought was a very nice sampling of the types of tasks that business leaders are looking to get from AI. What are the benefits that they want from AI? So 38% said predictions on activity related to machines, customers, or business health. Right, so can you predict for me which customers are going to churn, which machine is going to go down, which insurance policies are going to have a claim this year, right? 27% are looking to automate some manual and repetitive tasks. So triage claim submissions away, for example, or take your most high-risk insurance claims and send them to a special processing unit. So automating some of that. Also things like natural language processing, right? You're trying to figure out customer sentiment or general topics that are talked about. Instead of having someone scan through that, you can automate that with AI. 14% are looking for monitoring and alerts, so things like waste, fraud, and abuse, right? Alert me when there's a fraudulent activity. 10% increase quality of communications with customers. So that's things like understand how my customers want to be reached. How do they want to be communicated through? And then you can automate that. So certain marketing campaigns can go through text for some customers, through phone call or email for others. 7% recommendations related to internal issues or customer facing. So it's familiar with Amazon and Netflix recommendation engines and providing additional products and services to clients. So that's just a sampling of the types of benefits that business leaders are getting out of AI today. So let's talk about how it works a little bit. This first slide might be somewhat familiar if you know the gist of AI. We're going to start with historical data, and I'm going to talk about something called supervised learning for a second. We'll get to unsupervised learning later. But in supervised learning, you have in your historical data some KPI that is important to you, like customer churn. You know when your customers stopped providing service or when they actually canceled the service. You know when a loan defaulted. You also know some information about that customer. For example, you have their loan application information. Maybe you have third-party data on demographics. Maybe you have their credit score brought in through third-party data. But you have this historical data, and you're going to start to apply machine learning to find patterns in all that information about the customer. What are the patterns that are associated with when someone does churn away from your business or when they default on a loan? Once you have those patterns identified, you can apply them to the future. So as you have a new customer and you don't know whether they're going to default or churn on away from your business, you can apply that pattern and get a probability of that. And you can ask various types of questions. What categories is how much, when, why, how certain are you? That's the general, very high level view of what we do with machine learning. So let's talk about those types for a moment. You can ask questions like how much or how many, and we call these regression type questions. So what you're trying to predict is a numeric value. So revenue forecast, for example, cost estimation. If you want to forecast how many students will enroll, if you want to predict how long your customers will wait in line for a service. These are regression type questions. And then we have classification. So what category does this belong to? 9 times out of 10, this is a binary yes, no, 0, 1 type of classification. Is this customer going to turn away and cancel their subscription? Is this loan going to default? Is this customer going to accept the promotion from a marketing campaign? So regression and classification make up pretty much the vast majority of machine learning in business. But it's not uncommon to have some other types of questions, like how do these things group together? You may be familiar with customer segmentation, which is, I kind of alluded to, unsupervised learning, and that's kind of what this is. It's not saying, I know that there's 3 types and I want to predict what type this new customer is. It's saying, what types are there out there? How many types? What are the groups of my customers? How do I understand my customers? What makes them similar or different from each other? And so it's a very exploratory approach that uses similar advanced technologies. The classic example is the marketing one that coined the term early adopters versus, I forget the other term, people like me who want to wait and see. We're called the king's out of technology, right? Before you go out and buy the latest and greatest, right? So there's those 2 types of customers out there. And customer segmentation is very common, particularly in marketing. Product recommendation is another type of clustering approach when you're looking at how do these things group together. You want to know if someone bought a particular product, what else are they buying that you could recommend that they would likely be interested in? And then there's which one of these is not like the others, anomaly detection type of questions, if you're looking for fraudulent activity or any event that happens very rarely. There's also reinforcement learning, which is less common, but what you're trying to do is optimize a series of actions or decisions. So each action that you, action point you come to has costs and benefits of different decisions, and so you can automate that path through a series of actions that way. So this is just a sampling of types of problems. Like I said, most come down to regression and classification, but the others are pretty common as well. So this high-level data science process. First, we discover the data, we manipulate the data, do some feature engineering, we train our models, we evaluate those models, and then we deploy them out there. And of course, long-term, we need to monitor, retrain them, keep them up to date. But what I'm going to do now is kind of take a step through each of these approaches. So looking at data discovery at first, you might be familiar with the big V's of big data. And in data science, you may be surprised now we don't actually need big data. I don't think everyone really knows exactly what big data is, but data volume, veracity, variety, and velocity are 4 dimensions that are used to describe what big data is. And in data science, I don't have like a cutoff of, you need X terabytes of data, and that's our classification requirement for data volume. Instead, these are dimensions that we go in and we evaluate and we think about just in a slightly different way, because it doesn't necessarily need to be big data, but it needs to be the right data, and we do look at these 4 dimensions. So data volume, we're probably more interested in how far back the data goes in history, and does it cover enough cases so you have enough customers, and what is enough? Is 2 enough? No. Is 2 million enough? Probably more than enough, right? And it's just about finding how much kind of going backwards is relevant. You don't necessarily need 10 years of data, right? Maybe 6 months is enough, maybe a year is enough, and it really depends on the use case. Data veracity is really, is it the right data? Is it meaningful data? Are there enough cases of all the different combinations of things? So if you think about one feature in your data set might be gender. So you have males and females, okay, do you have enough cases of each to detect a difference between them? Probably. Now, do you have enough cases when you break it down to customer type? So maybe there's subscription and maybe there's guest buyers. So you need male subscribers, female subscribers, male guests, female guests, right? So now your counts in each of those buckets is getting smaller. Now, if you think about having, 100 or more features, those buckets get smaller and smaller. And so when we talk about having enough data and having enough data across all of these categories and having the right data, that's kind of what we're looking for. Data variety, we want to know all the different sources. We want to know, are they structured sources? Are they unstructured? Is there third-party data? And also the topics, like anything with customer analytics, you want to have the 3 key dimensions we talk about a lot are demographics, behaviors, and attitudinals. So behaviors are what people most commonly have in their database. You have your interactions with your customers. You know their buying patterns. Those are their behaviors. Demographics, sometimes businesses don't have that, but there are third-party data sources available where you can bring that in to better understand your customer. And then attitudinals often comes from like social media. You know, who are these customers? What drives them? What motivates them? All of these things together give you a more well-rounded sense of your customer and help you anticipate their buying patterns and changes in their buying patterns. Lastly, we have data velocity. No requirements for data science. It can be a one-time batch score or it can be real time, but that's important to know and to assess how quickly is this data coming in. Is this Amazon where purchases are happening every microsecond? You know, is this higher education enrollment where you want to score this, you know, 2 or 3 times a year? So that's kind of what we do with data discovery. We're looking at data sources, the amount of data, the velocity, the meaningfulness of that data. And then we need to treat that data and extract some features. So I did put this table up last week when I was talking about building a feature store, but this gives you a sense of some of the functions and examples that we do during feature engineering. And as I said last week, this can be up to 70% of the effort, right? You need to extract features from all those different sources. So that top row is a good example, just computing aggregate features, the average purchase amount per month, total sales per quarter, average credit utilization, maximum days overdue last year. Those can be features in a number of different models that you'd be doing. You might need to bin them, to treat them. Things like one-hot encoding, normalizing data, cleaning it, and creating polynomial features. Those might be specific to which algorithm you're going to use, and we'll talk about that in a second. But some algorithms are stricter than others, and you need to make sure that you're following some of their rules. And so you need to treat the data to make sure it's appropriate for modeling. Ultimately, what you want is one single table for machine learning. So you have to take all of your data sources. Sometimes that's 30 tables, sometimes that's more, sometimes that's 5 or 6 different data sources, and you're doing all of that cleansing to ultimately come down to one single table where you have one row per observation. And that observation might be a customer. If you're trying to do customer churn, it might be a timestamp, a moment in time, like every minute you might want to score this and predict whether or not an event is going to happen. It could be a customer visit, so or a claim. But you've got to have it at that clearly defined unit of analysis. You've got your target in there, clearly defined. This loan defaulted or it didn't in this case. Then you have all the features about that target and about that observation. So age, credit score, for example. I didn't go through this in too much detail this time, but one-hot encoding is where you take a categorical feature. Maybe there's 3 different types of customer, and instead of having one single categorical field, for a lot of algorithms, you have to perform what's called one-hot encoding, which is creating one row per category, and it's just zeros and ones. Lots of zeros and ones in this final table that you're going to use. But ultimately, this is going to be a very wide sample, right? One row per analysis, and you get one prediction for each row. So that's the goal. Now you're ready to train your model. So you have to pick an algorithm, not just one, because you're probably going to test a lot of different approaches to see which one's best. And I'm not going to go through all of these in detail. A few things to point out is just that, like I said, you probably want to take some in different categories and test them out and compare them to each other. Some of these are only appropriate for specific types of machine learning, like whether it's classification or regression or clustering, for example, and sometimes you can use them across. So regression type questions, you can actually use regression or decision trees or ensembles or Bayes. So one thing I wanted to point out is regression algorithms up here in the top left. These are your old school classic academic type of algorithms. You probably learned in college at some point how to do regression. These are still fairly popular because probably more people know of them and have heard of regression or are familiar with it. Also, they're pretty transparent. As long as you understand regression and you know what you're looking at, you can really dig into the analytics that come out of that model and understand what's happening. Whereas a neural network is very, very black box, right? So your decision of which algorithm might be driven by how much do I need to pull out of this model? How much do I really need to understand it and pull some insight and provide that back to the business? The problem with regressions is that these are probably some of the least flexible models. There's a lot of rules. Any statistical-based modeling approach has rules to it. And if you break those rules, you risk really misunderstanding the outcomes, especially if you try to use that transparency and look at those weights and coefficients in there. You could be misunderstanding them if you didn't have the right distribution, or you didn't do that one-hot encoding, for example. So if you wanted to use like decision trees, neural nets, things like that, you have a little bit more freedom. You're not going to break things necessarily by just throwing it in there. But again, it's going to be a little bit harder to interpret what's going on. So there's those types of approaches. Dimension reduction, sometimes this is used as a feature engineering step. Actually, it's a model to predict or to reduce some, if you had a category with 1,000 options and you want to reduce that to some hierarchy, you could use dimension reduction methods to do that. And so you have a model within a model, essentially. And then there's deep learning that a lot of people are familiar with. I've seen a lot of reports that deep learning actually gets overused. It's the big, exciting, sexy thing. Everybody wants to do whatever's new. But it's very computationally expensive. And so you may be overdoing it. Parsimony is key when you think about building models. Parsimony means, go with what's simplest. These regularization algorithms here are actually designed to do that. They're regression based, but they kind of punish models that are more complex than they need to be. And they help you kind of weed out a lot of the parameters you don't need. You want the simplest model for the most accuracy, but you don't necessarily want to take the most accurate model that takes 8 hours to run, for example. So that's just something to think about. So then you need to evaluate your model. This famous quote, all models are wrong, but some are useful. The first question that businesses want to ask data scientists is, well, how accurate is the model? And that's actually a more difficult of a question than most people think. And it's not that the data scientist is being cagey and struggling to answer it. It's that the answer to that question depends on our tolerance for error and where that error needs to be. And so I'm just going to demonstrate that with this. It's called the confusion matrix. You may be familiar with this. So essentially, if you were to plot your predicted cases, those that were predicted not to be, for example, a lone default versus that were predicted to be a lone default, and the rows are the actual not defaulted and really defaulted. And so we have true negatives, true positives, and then our false positives and false negatives. So let's look at one example where you have 100 cases, 100 loan applications, only 5 of those defaulted. And maybe after we train our model, this is the result. What you see is that this model never detected any of those to be a lone default. But this model's accuracy is 95% because 95% of the time it was right up here. And so you see in these what are called imbalanced cases where your target happens very infrequently, your overall accuracy metric and many of the other metrics that we use to evaluate models are really inflated, right? And that doesn't really help us because the model never detected what we wanted it to detect, even though it's 95% accurate. So instead, we want to look at a few different things. So let's look at this case, first of all, where, again, there's 100 cases. 50% of the time they did not default and 50% of the time they did. The model predicted 45 of them would default. We were wrong about 5 of those, and we also missed 10 that actually were defaults, and the model didn't pick them up. So in these kind of cases, what we want to look at are things like sensitivity and precision. So sensitivity is the percent of the actuals that we were able to find. So in this case, we found 80% of the loans that defaulted. And the other way to look at this is precision. We found 89% of the cases that we said would default actually did default. So it's just 2 different ways to look at something. Now, which is more important depends on your business. Is it more costly to have a false positive, or is it more costly to have a false negative? Sometimes you just want to cast a wide net and you want to get all potential cases. So we did this with claims post-payment recovery, right? We want to know, is there room to recover some funds? And so we just want to identify where there could be not necessarily fraud, but some kind of error, right? But there's a cost to investigate each of those. And so there's an actual financial cost with getting it wrong. Sometimes, though, you'd rather spend that cost and not miss these ones where you could actually recover some costs. And so there are ways to tweak this, and you're not actually tweaking the model, you're just tweaking your threshold for where you push your error, right? Because essentially the error rate is there, and it's do you pile it into false negatives or pile it into false positives. So in general, about machine learning evaluation, it's kind of a data scientist and business decision to talk to each other and to understand the impact of the error rate and where you want to go with that. And then eventually you want to move to deployment, right? Hopefully you get that model, it looks good, you want to get it out into the business. And this is just really a rough example of the data pipeline, because that's what deployment is. You trained an algorithm. Through all that machine learning, what you did was you came out of it with a final single algorithm. And if we use a regression, that algorithm would look like this: y equals mx plus b. If you go all the way back to your college algebra classes and you remember the equation for a line, you're actually going to have sitting somewhere y equals mx1 plus b mx2 plus mx2, mx3, etc. And what you want to do now, you pull in new data, you run it through all that feature engineering process as it was defined during your model training phase, and you're just going to plug it in over here into your algorithm and solve for y. And then you're going to take that y, which is the probability that a loan is going to default, and spit it back to the business so they can use it and make a decision based on that. Right, but this whole process of building this pipeline and this automation is a whole nother step on top of machine learning. And so that's why I kind of separate machine learning and AI. Machine learning is training this algorithm, creating it, and then AI is building this entire pipeline to plug it in. So that's a lot of kind of information. Just to give you some key takeaways here, machine learning and AI, they represent the step beyond traditional business analytics into a deeper, more advanced approach to BI. We're going to leverage historical data to find those patterns. And once we've created those patterns and established them, to make predictions or estimates about the future. There's different types of machine learning and different types of business questions that can be addressed. So I hope you've got a bit of a sample of those. Feature engineering is the most time intensive, I mentioned that, but it's also the most important. It's important that you pull as much data as you can, as many features as well-rounded and multidimensional of an approach as you can to best understand your KPI. When selecting algorithms, remember KISS, which stands for Keep It Simple, Stupid, sorry. Throwback to my grad school days, that was drilled into me, right? You don't need to be overly complicated just for the sake of being complicated and exciting. You really want to go with a simpler model and parsimony. Model evaluation is not standard and really needs to involve the business SME. So you want to do that together with each other because there's really not one standard approach. There's many, many different metrics and ways to evaluate models that depend on the use case. It depends on the distribution of your target, depends on how you're going to use it and your tolerance for error. So let me pause it there and open it up for questions. So I think Debbie will unmute so that you can self-unmute if you would just want to ask questions, and you can also just type up any questions in the chat box and we can answer them.
And one is, we talked a lot about in previous about data enrichment, so I think you will have an answer to this one, but is there such a thing as too much data?
Too much data, so it depends on whether we're talking too much in terms of features or too much in length or history. So I've said over and over that you want as much data as you can. You want as much information about that customer if you're doing customer analytics, about that process if you're studying a process. You know, people especially are very dynamic and unpredictable, so you want as many features as you can. But historical, you know, if we'll often use 1 year of data or 2 years of data. You may have 10 years in your database, but if you think about how things were done and the meaning of those data and the patterns 10 years ago or even 5 years ago, or 3, it's different. And so by including irrelevant data, you could actually be hurting your model because it's trying to fit patterns that aren't relevant anymore. And so depending on the use case, we tend to limit that kind of history, and often, very rarely will I go back more than 2 years.
Thank you, Pam. Another question, on average, how long does it take to train a model? Is it a couple years, more?
No, so the actual model training, it's sort of anticlimactic when you spend weeks and weeks doing the feature engineering, and then you can train a model with a few lines of code and it can be instantaneous. Deep learning models, you'll probably run those overnight. So once you've actually trained them, then there's evaluation and there's back and forth, and you want to do different models. So I'd say it's a few weeks of effort to evaluate it before you're ready to deploy. But the actual moments of training, it could be seconds, or it could be many hours, depending on the algorithm, the amount of data, the intensity of the features.
Terrific. And one last question, where does continual learning come in?
Oh, that's a good question. So here, I didn't really talk about that, right? Once you build your algorithm and you store it somewhere, and then you call it as whatever your schedule is, real time or in batch, you do need to update it and training. And so the outcome is going to go back into the business, but then the results and the impact of that need to go back into your database and back through another process. I don't have really outlined on here, but there'd be retraining. And so that can be manual, like, hey, we haven't retrained our model in a while, let's go in there, it's been 3 months, let's retrain it and evaluate the changes. Or it could be part of your automatic pipeline here. Maybe it needs to be retrained every time you score it. So it depends on the use case, but it should be part of this. It's probably too often that people train it, deploy it, and then don't retrain it either manually or automatically. But that continuous learning is kind of when you automate the process of, score it, send the predictions, and then automatically retrain to improve the model.
Terrific. And I think since our 30 minutes are past, we'll just keep this as a continuous conversation. And if anyone wants to talk one-to-one with you, they should take advantage of that.
Yes, thank you so much. And we'll talk to you next week. And we'll have Data Robot sharing their MLOps platform next week.